And I'm going to talk about private AI. And let's start by a story. Imagine you just finished training your model. Oops. And you just feel on top of the world. You train a model that takes DNA sequences and can make all sorts of predictions, right, about diseases, about what kind of food will make you happy, whatever. And your model is just amazing. You test its accuracy, AUC, specificity, all the metrics are just fantastic. And all you see in your mind is this, right? You're just going to put it as a web service out there, and the money will just start flowing in, right? And you put the web service out there, and no one uses it, right? And why? Why? Right? Now, imagine it was me that built this service, and I put my service out here and tell you, please give me your DNA sequences, right? Now, you know, we know each other. We already know each other for 2 minutes. Don't you trust me with your DNA sequence? The reality, and we just heard about it in the previous talk, is that you shouldn't. Yeah, the picture is so good, it wouldn't move to the next slide. The reality is that this kind of situation happens a lot. Whenever you do something with genetic data, medical records, financial information, behavioral information, these are sensitive data. And people are and should be careful about the way they handle it. And the question that we want to ask is whether we can generate this kind of services that will deliver the value while maintaining the privacy of the data. And the answer is that we can. So what we can do is do something like that. Imagine, go back to this DNA classifier that we've built. We're going to build it in a way so that you take your DNA sequence, encrypt it. And when I mean encrypted, I mean real encryption. I'm not talking about some pseudo encryption. I'm talking about real strong encryption. You send it to the service on the cloud, just the encrypted file without the keys. And on the cloud, the data is being processed, the model is being evaluated on your data, and the result is sent back, but everything is maintained encrypted. So the service that sits here in the cloud, not only that it doesn't see your DNA, it doesn't even see the prediction that it made on your behalf. And the only thing that it can do is send it back to you, you decrypt it, and get the result. So this is what we do, and I'm going to spend at least the first half of the talk explaining a little bit about how we do that. But just to make sure that we're on the same page, the cloud cannot read the data, so the cloud doesn't learn anything about your DNA. The predictions are accurate, and the cloud cannot read even the prediction that it made. So this is what we're trying to do. And basically, we're going to talk even about a broader set of problems which involve collaborations with data. So at Inference time, which was what we talked about so far, was about we have one party that has a model, the other party has data, and we want to collaborate somehow. Or a training where we have maybe multiple parties, each one of them have different part of the data and they want to do something together. So all these settings require some techniques to allow collaboration. And collaboration can be easy, right? It can be easy. So if we, for example, want to train data on distributed data, I can tell Kostya, Kostya, send me your data, right? And Kostya will send me his data, and that's easy. But in many cases, you cannot do that. It's maybe because of a regulation. So if you're handling medical data in the US, you have to comply with HIPAA rules that tells you how you should handle the data. GDPR, probably many of you know about GDPR, the European rules about how to handle data. There is competition. Maybe Kostya and I are competing right? Maybe we want to build a model together, but Kostya doesn't want to share his data with me because it has some other values that he doesn't want to share with me. So there are a lot of constraints when we try to do something in collaboration. It's not very cooperative. Yeah. So whenever you're trying to do collaborations with constraints, this is where you want to use encryptions. And we're going to show you now how we do that. So we'll start with private inference. So again, this is a model that we talked about before, right? We have one party that has data, the other party has a model. We're going to encrypt the data, send it to the model, and evaluate it. And the secret sauce to doing that is a technique that is called homomorphic encryption. So it's easy to demonstrate homomorphic encryption with this cartoon. And imagine you have a piece of gold, and you want to give it to a jeweler to build a nice bracelet or something like that. But you worry that the jeweler might take some bites off your nice piece of gold. So what you do is you place it inside this kind of a box. The jeweler can still work on the gold via these gloves, but the box is locked. You are the only one that has the keys, so he cannot steal your gold. And once he's done, you come with your keys and you take it. We're going to do the same thing where instead of gold, we're going to have data. I'm going to lock it with encryptions. And some people say that the kind of encryption that we're going to discuss about is actually misspelled. It shouldn't be homomorphic encryption. It should be homomorphic encryption, after Homer Simpson that used this kind of box.
Mr. Burns.
Sorry?
Mr. Burns.
Yeah. So what does homomorphic encryption do? So imagine you have two numbers, x1 and x2. Obviously, you can add them and then encrypt them, right? That's something that every encryption allows you to do. But homomorphic encryption allows you to go the other way around. So you can first take the numbers, x1 and x2, encrypt each one of them separately, and then compute the sum of these numbers. So again, just to explain, to make sure that we are all on the same page, imagine that I have two numbers, one on each hand, but they are inside my fist, so I can't look at these numbers. But I can do a certain operation by which I will end up with the sum of these numbers still in my fist. I still cannot look what the result is, but I know it's a sum of these two numbers. So this is what we can do. And another thing that we can do is the same thing for multiplication. So we can take two numbers, multiply them, and encrypt. But we can also go the other way around and first encrypt and then multiply. So homomorphic encryptions allow us to do both addition and multiplications on encrypted data. And actually, the idea to develop homomorphic encryption was something that was suggested in the 70s. And the reason why it was so interesting is because basically with homomorphic encryption, you can take any Boolean circuit, anything that you can express as a Boolean circuit, and compute it over encrypted data. Why? Because basically multiplication is equivalent to the AND gate modulo 2, addition is equivalent to the XOR, and these are complete. So every Boolean function can be expressed using AND and XOR. So in theory, if you can implement homomorphic encryptions, what's called fully homomorphic encryptions, that means that you can take practically almost anything we do with computers and now run them over encrypted data. So it was something that was looked after since the 70s, and only about 10 years ago, it was the first time that someone managed to really show that it's possible to implement that. But there is still a problem. As I hope many of you know, that only in theory there is no difference between theory and practice. In practice there is. And the problem is that although we're fully capable of implementing homomorphic encryptions today, they are very slow and memory hungry. So if we just take something as simple as, say, multiplying two 32 bits numbers and just write it as a Boolean circuit, the process of multiplying two such numbers, it will probably take something of the order of 1 megabyte of memory just encrypting each one of these numbers. And then the computation will take about 10 minutes just to multiply two numbers. And what we are aiming at is implementing neural nets over encrypted data. That doesn't seem very feasible. So the main challenge is actually doing operations over encrypted data, but keeping it efficient. So the first step was to create a library that implements homomorphic encryptions. We created this library. This is, by now, we already have, I don't know, it's version 3.3 now, I don't remember. And the idea of this library is actually not only that it implements homomorphic encryption, actually to make it relatively accessible to using it. And when we publish it, somehow all sorts of bloggers found out about it. And one of them was really creative. I'll let you read it for a second. Okay, so they were suggesting that homomorphic encryption is something that some more conservative people would not appreciate, and we should have heteromorphic encryptions, but we're still working on that. But anyway, with this library, we made the attempt of applying neural nets over encrypted data. And this is a project that we called CryptoNets. And we used the almighty MNIST data set for that. So just to make sure that we're all on the same page, so neural nets, basically you can, neural net has this kind of a structure. You have an input layer in which you have your features, and then they move up, right? Nowadays, somehow neural nets started moving from left to right, but it used to be that they move upwards. Anyway, at each layer, each node gets its input from the lower layers, and basically what it does, it computes, first of all, some weighted sum over its inputs, and then applies some nonlinearity. So how is it clear for the audience here? And now we want to do this computation, but over encrypted data. So let's look at it for a second. So first of all, for our application, the inputs are encrypted, but the weights on the matrix shouldn't be encrypted, because if Kostya sends me his data is going to be encrypted, but I know the network that I'm going to apply to his data. So if I know the network, the weights shouldn't be encrypted. And that already gives us some benefit, because when I'm doing operations between encrypted data and non-encrypted data, I can actually make it faster. Yeah.
Why shouldn't the weights be encrypted?
You can. It will just make things slower. Because if you send me your data, and I have a model, you have the data, right?
Yeah.
I know my model. I don't have to hide it for myself.
Yeah, but isn't the weights is what we're trying to find out? But if we're looking at the generative.
No, so imagine we're now at the inference phase, right? I have a model. And you want me to apply my model to your data. So I know my model. What you're trying to hide is your data, okay? And we could also do the other way around. So it could be that I'm sending you my model, but I don't want you to learn anything about my model. But in which case, I'm going to hide the weights of the model, but you know your data. So you shouldn't hide it from yourself, right? So first thing that we can do is to note that actually, when we do all these operations, the xi's are going to be encrypted, but the wi's are going to be in plain text. Next, if we look at the So let's start by looking at this operation. This operation is just sums and multiplications, right? And as we saw before, sums and multiplications are something that neural nets can, homomorphic encryption can support, so that's not a problem. The problem is when we try to apply nonlinearity, right? So typical nonlinearity that we apply, things like ReLUs or sigmoids, they are not just sums and multiplications, right? And with homomorphic encryptions, you can only do sums and multiplications. So what do we do about that? So let's look at these functions and let's try to understand what is the essence. What do we really need out of them in order to make the neural network work?
Generate sum and multiplication.
Sorry? So with sums and multiplications, we can only compute polynomial functions, right? The class of functions that you can evaluate with sums and multiplication is polynomials, and these are not polynomials. But our true requirement of activation function is to be nonlinear. So why do we have to have nonlinear activation function? What would happen if we just use a linear activation function at
only one layer matrix.
Exactly. So the entire network will kind of collapse. I can express it just as a one-layer thing. So I'm not benefiting from the depth. So that's the main constraint that I have from kind of machine learning point of view, is that I need some nonlinearity. But from crypto point of view, my main constraints are that the activation function has to be a polynomial, and I want it to be a low degree polynomial. Why low degree? Because in homomorphic encryption, additions are relatively cheap in terms of computation, but multiplications are expensive, especially when I apply multiplication over multiplication. Kind of the degree of the polynomial that I'm computing, I pay a big penalty for that.
And you can have nonlinear stability.
Sorry?
Problem. You're going to run inside the numerical non-stability
True.
problem inside.
True, but kind of I'm trying kind of to look at only the very essential constraints that I have, right? So the very essential is I'm looking for an activation function which is nonlinear, it's polynomial of low degree. So what is the lowest degree polynomial which is nonlinear? Square. So we just use the square as the activation function. So we build a neural net that instead of ReLUs or sigmoids, we use square as the activation function. So it's nonlinear, but we can compute it with homomorphic encryptions because it's polynomial and it's of low degree. And it turns out that it works. So it took us a lot of iterations. Our first attempt, and I'm talking about MNIST, right? So it's we had the network with an accuracy of 97.3, and it took us 20 minutes to make a single prediction, right? So, you know, that's kind of our starting point. And via all sorts of improvements. So for example, this one is just looking at the fact that the weights are not encrypted, only the data is encrypted. We got down from 20 minutes to 20 seconds. And then all sorts of ideas. We got it to work in about 5 minutes with accuracy of 99%. Now again, when you think about it, you know, 5 minutes for a single prediction, you know, I can make it with a, you know, a Casio FX82 calculator. I can probably do it faster. But, you know, we have to compare apples to apples, right? You can't compare making predictions on encrypted data to making predictions on plain data. For example, imagine it was your DNA sequence and you go to your doctor's office and your doctor tells you, look, I can either, I have to get your data evaluated. I can either send it and get the result just in, a fraction of a second. But it will be, I'm just sending your DNA out there to the world. Or you can wait 5 minutes and get the assurance that your data is still private. Are you willing to wait for 5 minutes in your doctor's office? At least some of you will be willing, okay? So when we make this comparison, we shouldn't make the comparison to, oh yeah, I have my new box with 8 GPUs and it can run it in, I don't know, it's in several nanoseconds. This was a breakthrough, right? So showing that you can actually apply homomorphic encryption to a practical problem was actually something that was a breakthrough. And actually since then we've improved it. We can now make such a prediction in 2 seconds. So now when I ask you, are you willing to wait for 2 seconds and to make sure that your data is kept private, I hope that a larger fraction of the audience will say that it makes sense. We can also do these days even more complicated tasks. So for example, we can look at, MNIST is kind of the simplest task of them all. But now we can look at a task like predicting objects from image. And here, it's we have about 100 classes. We can get to 80+ accuracy and make a prediction in a fraction of a second. It's a little bit cheating because we're using kind of transfer learning here. But still, the idea is that it's becoming more and more realistic to use these kind of tools. So before I move on, there were some questions. Let's
You mentioned in the beginning that you also keep the labels private in a way. And
Yeah.
So how in this case you can preserve the privacy of the label itself? Because I think this is the main information that me as a patient want to keep, because it might contain some private information about what I have.
Sure. So let me just repeat the question. So the question was, how do I keep the label private? Not just the input data, but the label. So let me go back and try to explain, because this is something important and I might not be explaining it well. So imagine this is your neural net and you sent me your data and it's encrypted now, right? So these features are encrypted. And now as I propagate the data through through this network, I do it with homomorphic encryption, homomorphic operations, meaning it's not only this data is encrypted, this is encrypted as well, right? But when I compute the weighted sum, for example, of these values, since they are encrypted, I don't know what the result of this weighted sum. I only have the encrypted version of this weighted sum. And when I apply the activation function, the x square, I know that I have applied x square. I know that I applied it to this data, but I don't know what the data is. I know that here there is the result of this computation, but I don't know what the result is.
But you know the output of your network, what each output represents.
But it's encrypted.
A higher number doesn't mean a higher number.
No, it's encrypted. No. It's encrypted. So just to explain how well it's encrypted, so, we all know that if ever there's going to be a quantum computer, then kind of many of the encryption techniques that are used today are going to become vulnerable. This does not apply to these kind of encryptions. So when people now are thinking about post-quantum encryption, they are thinking about these kind of techniques.
But sorry, but if you use argmax on the Y output and then you select Y2, which represent certain label, doesn't mean...
I don't apply argmax because I don't know how to apply argmax. I just sent you Y1 and Y2 encrypted, and only you that have the key can decrypt it. Okay? It's really, it's, I have to, let me tell you a story, right? Maybe that will help. When we just started working on that, So a student of mine came with kind of the vague idea, and I just wrote the proof that it's impossible, right? And obviously I was wrong, and the reason why I was wrong is because everything is encrypted. So if the data is encrypted and I can see y1 and y2, basically I can learn something about your inputs. And that means that this encryption is just, it doesn't work, right? But the reason, in a sense, why it works is because everything is encrypted, including the output. Another question? Yeah.
What's about federated learning?
We're going to get to that in a second. Good. It's by definition, this is a great question because we're going to get to that. I have slides about that. Yeah. Yeah.
About one slide later, you have your homomorphic models, and no, another slide later. You have those models that relied on, like, try to measure both the accuracy and the latency for different models.
Yeah.
Right here. What exactly were you predicting?
So here it's the MNIST data set. So you have images of handwritten digits, and you're trying to predict what digit is it. So you have, let me go back and you'll see, just a second. Okay, so you have this kind of an image, but it's encrypted, meaning that you get every pixel is just encrypted, and you're trying to say whether what is the digit that is written here. Okay, this was a task. Actually, one thing that I didn't mention here, let me go back to these numbers. So you might see here something funny, that we go from 24 seconds to kind of our final version, which is slower, doesn't make much sense. It has better accuracy, but not only that. Actually, this version can operate simultaneously on, this one I think is 8,000 images simultaneously. And the reason is homomorphic encryptions, many of them, the one that we use here, actually operates on vectors. The input is a vector, and when I'm doing addition is actually element-wise addition, and multiplication is element-wise multiplication, which means that I can stack together, since the vectors in this case is, each vector is at dimension 8,000, then I can stack together 8,000 images. So I can put in the first column the pixel from the first image, in the second column the pixel from the second image, and so on. And the network will just operate on all of them simultaneously. It's much like SIMD, if you're familiar with the way GPUs operate. And again, to give you a sense of what kind of security it gives, me as the one now running the model over your data, I don't know how many images you put in the data. I cannot tell whether you send me just one image or 8,000 images. I just can't tell. Yeah.
But does the client, the end user, have some kind of last softmax, something to do with the logic after decryption? I mean, he needs some additional logic, right?
Yeah.
He doesn't have a final label.
Yeah. Yeah. You just get, in this case, you will get 10 numbers and we'll pick the largest one. That's kind of the computational cost for the client. Yeah. Yeah. So other tasks are, some tasks are, if it's regression, then it's easy. If it's for other tasks like reinforcement learning, it's hard and we don't know how to do it. Yeah. Can you try to?
In case you don't know actually in production, what are your outputs? What is your framework to work with production? For instance, to be sure that distribution of data that you get from clients are similar to distribution of data that you train.
Okay, let me try to repeat your question. So the question that was asked is, I was training over, I'll try to repeat to make sure that I understood your question. Maybe I trained over one distribution and then you send me images from a very different distribution. How do I tell that it's actually out of my kind of comfort zone? And I can't. I can't see your data. I really can't see your data. Right? So let's take the last one and then we'll keep going. Yeah.
Can you learn from encrypted data?
That goes back to the question that was asked before. That's a great question. But
can you get any idea about the effectiveness of the algorithm?
I cannot, again, when let me just answer this. The question is, can I learn something about the effectiveness of the algorithm? So I hope that I understand correctly your question. If I put aside encryption, say I just put a web service that makes prediction, it makes sense that I have something out there that looks at my accuracies of the predictions, and maybe there is a circuit breaker that goes off if I see suddenly that things doesn't behave as I expect them to behave. And it goes back also to the question that you asked. Maybe people are sending me images that are not the kind of images that I was expecting to see, and that might be a signal for me that I need to retrain or something like that, right? In this case, I can't. I really don't see your data. I really don't know if I made good predictions or not. I'm trying to keep your privacy. And really, there is a price to be paid. Part of the price is the time, right, the computation cost, and part of the price is that I cannot give you some all sorts of safeguards, in a sense, that things don't go wrong, because I really can't see your data, right? So let's keep going, and maybe we'll get back to some questions later. So before we get to the training part, and I promise we'll talk about training, let's talk a little bit about privacy and ask ourselves, where do we want to have privacy, and what kind of privacy do we want to have? So first I want to say something which is important, and I'm going to say it and then drop it. But actually, the entire thing that we call privacy is completely wrong, including the things that I'm talking about. So, when you say that you have a private car, what do you mean by that? Do you mean that I can't see your car?
No, you can't use it.
What?
No, you can't use it.
I can't use it. Exactly. Privacy is about agency. Privacy is about your ability to decide what to do with it. The fact that I have a private car means that I can decide what to do with it. I can give you the keys to the car. I can decide not to give you the keys to the car. But it's not about not allowing you to see my car. That's not what privacy is about. While we in computer science, usually when we talk about privacy, we talk about not being able to see your data. But please keep in mind, if you work on applications that work on private data, that it's not just about being able, to keep it private in the sense not being able to see it, but it's also allowing the user to decide what to do with his or her data. So having said that, I'm going to drop it and keep on talking about hiding data. So actually we are very familiar, all of us, with all sorts of places where we kind of have private data and we use encryption to hide it. So for example, when you browse the network and you go to your online banking account and you see this HTTPS, right? You know what I'm talking about? Right? That means that there is some encryption going on, and basically that is encryption on transit. So when I communicate with my online bank, the bank gets to see, the bank knows how much money I have in my account, right? The only thing that we're trying to protect against is against some eavesdroppers that are going to listen. I don't want maybe my service provider to know how much money I have in my bank account, right? So that's encryption on transit. We also have an encryption on at rest, things like BitLocker or things like that encrypt the data while they're stored on my disk. But once they are loaded to the memory, There are decrypted and there are in the clear. Right? We're on the same page? None of them keeps the privacy of the data during computation, right? When I communicate with my bank, the bank sees my data. When the data was encrypted at rest, but when it's loaded up to the memory, it's in the clear. All the computation is done in the clear.
There are solutions to that.
There are solutions, but these solutions do not provide any. Yeah. And now we have all sorts of solutions that focus on keeping the data private during computation. So we talked about homomorphic encryptions, but there are other techniques. I'm just going to go about them very briefly. So we have MPC, secure multi-party computation. These are techniques that it's kind of protocols by which if you have multiple parties that want to do something together but without revealing their secrets, so they want to compute some value without revealing their individual values, you can run these kind of protocols. Kind of the canonical example is, imagine that we want to compute together, say, our average salary, and we agree that we're willing to share the average salary of all the people in the room, but I don't want to share my salary with you, right? Kostya, do you want to share your salary? No. Okay. So the idea is that we can run these kind of protocols by which we're all going to discover the average salary, but we're not going to learn individual salaries, right? So this is MPC. Secret shares is another version of such protocol. SGX, and it goes by other names. These are technologies that there are hardware technologies in which you have kind of a secure place inside the CPU that only the data gets decrypted only inside this secure place. So the data is encrypted everywhere else, only inside the secure place. The data is decrypted. The program runs on your data and then encrypted again before it goes out. So we have all sorts of techniques to allow you to keep the data private during compute. But they don't secure the data after the compute. So what does it mean? So imagine we computed together the average salary of people in the room. Accidentally, we know that Satya Nadella was really interested in this talk, and he's in the room. So now I don't know all of the people in the room, but my guess is that Satya has much higher salaries than anyone else in the room. And just by knowing the average salary, I can guess something about his salary, right? Kind of, you see what I mean? And actually, there is something important here to keep in mind. I know, but let me give an example, right? If you would, yeah. But let me give you a version of it, which will, I think, maybe make better sense to. So imagine Satya was on a visit in India, and there is a rumor that he was hospitalized, right? He was visiting some rural place, and there is a rumor that he was hospitalized. So you go to this hospital and ask them, what is the average salary of people in the hospital these days, right? Just by knowing this average number, you know whether Satya was in the hospital or not. And imagine what happens to Microsoft's stock at this moment, right? So the thing, and it's important when we work on privacy, a lot of things goes wrong when you have side information. If you look at many of the familiar cases, like the Netflix challenge data, familiar with the story, how data leaked from over there? Familiar with that or not? No? Okay, so it's a nice story, so I'll tell it. So Netflix challenge, everyone is familiar with that? No, okay. So Netflix, a while back, a long time, it's about 15 years ago, I don't remember exactly, they released some data, anonymized, with you just had, imagine you had just, a user ID, names of movies, and thumb up, thumb down, right? And the reason why they released this data, they did a competition with, they put the winner would be awarded $1 million, I think, was the prize, just for building recommendation systems, right? And actually, Israelis won this prize. And then it was very successful, the competition. Many teams around the world participated. They got much more work that they could have ever gotten for $1 million. And they wanted to run a second round. But by the time they got to that, people started releasing names of people whose data was in the data set. But you know, how could this be done, right? So you have just user ID, just a random number, and summed up, summed down for some movies. The reason is people started doing correlations between that and some other public data sets. For example, with IMDb. So suddenly you see that there is a user that gives summed up to, I don't know, some Sylvester Stallone movies and to Bambi. And you see in IMDb a user with kind of the same favorite movies. You kind of say, okay, this is the guy, right? Another example, how many of you remember AOL as a search engine? Remember that? So AOL, right, sorry? America Online, right? They used to be, you know, one of the bigger players in the search industry. Yeah. And again, they did the same thing. They, for research purposes, they released some data. So again, you had some user ID, some just random number, and the queries that they made. Fully anonymized, right? It took 2 days to have a headline in the New York Times with a name of one of the people. And they could have found her really easily because they found this user was first of all making searches about all sorts of places, all sorts of kind of, where is the library in this town? Where is the grocery store in this town? Okay, she lives in this town. And then she was making queries about several people with the same last name. So they guessed that she's probably looking for relatives. So they guessed, okay, this is her last name. And then she was also looking for bachelors at the age of 60 to 65. So you kind of know her age, right? You kind of know where she lives, and you kind of know her last name. So now you look just at the names of people in this town, and there was just one person qualifying for these all these qualities. And then you look at other searches that she was making, and she was making searches like what to do with a dog that pees on the sofa, right? So all sorts of kind of things that I don't know if you wanted to make public. But again, the thing is that a lot of problems of data leak, actually almost all of them, are due to side information. And I can give you a lot of other examples of that. So we want to keep the data secure, not only during computation, but also after computation. So if we release our average salary, we want somehow to be able to prevent people from doing some reverse engineering and from the average salary, learning about my own salary. So imagine, you know, let me give you another example for the average salary. Imagine we compute our average salary, and now as I go outside for a second, you run another round of computing the average salary, right? Right? So now you know my salary, right? Lucky enough, I'm in the academia, so it's. So, I think that we have also all sorts of techniques, and the main one is differential privacy that works on protecting data after computation. And in a nutshell, what differential privacy does, it adds some noise to the result to prevent the ability to do this kind of reverse engineering. But this kind of a map of where do we want to have privacy at? We want to have privacy on storage, on transit, on compute, after compute. And whenever you design some system and you want to take privacy into consideration, you have to decide what is relevant for the system that you're building. Another thing that you have to keep in mind is what is your source of trust? Who do you trust? So for example, you might say, you trust me. So if we want to compute the average salary, just everyone will write on a note, just hand it to me, because all of you trust me, right? Is there anyone in the room that doesn't trust me? Okay. So that's, sorry? I didn't ask this question. So, but in some cases it makes sense, right? So we have someone that we all trust, and we can use that. That's a source of trust. In some cases, we trust some big entities. So we say, okay, Google, Facebook, choose whoever, this big company, and we trust them, or maybe the government, and we trust them. In some cases, we say we trust mathematics, and we use encryptions. And we also have to think whether parties are honest or malicious. Honest or malicious are, honest is usually someone, I'm not going to trick you. But if you're going to tell me one of your secrets, I'm going to be happy to use it, right? So it's much like, look, I'm not going to break into your house in order to steal money. But if you'll leave a note on the table, a 200 shekel note on the table, I'm going to put it in my pocket, right? So you have to decide whether you're trying to protect against someone that will just pick a note on the table, or against someone that is going to try to break into your house. That's not the same thing. And the last thing, and we talked about it, is whether you consider some side information that people might have, and you want to be safe against that as well. So okay, that was kind of a side note about privacy, and now I'm going to go a little bit about training. What do we do in training? And again, the interesting setting for training is not where I have my data and I want to train, but I want to do the training on the cloud. So, how do I protect my data in the cloud? The more interesting setting is where actually you have multiple parties. Each one of them has some part of the data, and we want to do something together, because this is where we have collaboration. And when we think about data being split between multiple parties, there are actually two kind of schematic ways in which it could be broken. So imagine in standard settings, our data is just like a big table, right? We have columns, which are features. The label is just a glorified feature, right? And we have the records. And one way in which the data could be split is that we have, say, multiple hospitals. Each one sees their own patients, but they want to train together to get a larger data set. In this case, the data is split horizontally, right? So we have one hospitals that have, these records. Another hospital have these records, right? So, and every hospital sees all the features of their patients. This is, for example, the setting in federated learning. Another setting is where we have kind of asymmetric parties. So imagine a hospital wants to train a model together with data from Facebook. Why? Because although the hospital has a lot of data about our medical condition, but they don't see what happens between visits to the hospital. If they want to see what happens between visits, they have to look at Facebook. But Facebook would not share their data with the hospital, and the hospital would not share the data with Facebook. So here, the data is vertically split. So we might have one party that sees these features. This could be the hospital. Facebook might see these features, and maybe we have another party that sees just the label. Okay, so this is kind of the vertical split setting. And we have solutions to both settings, and I'll just go about them very briefly in the interest of getting home sometime. So for the horizontal split, it's basically same idea being used by federated learning. And the idea is that if you look at many learning algorithms, they're basically gradient descents, right? A lot of our learning algorithm, obviously in neural networks, but actually in even gradient boosted trees can be viewed in this setting. And what you do at every point in time, you have your set of parameters that you trained so far, and you want to compute the gradient of your loss function which with respect to this parameters. And you compute it for every data point, and you sum them up, and then you do a gradient step. So first thing, in order to make it differentially private so that we can prevent this reverse engineering, what we do is when we compute the gradient, we add some noise. And the second thing that to note is that when we compute this gradient, it's the sum over gradients over all our records, and we can use MPC. So remember we talked about computing our average salary? Computing the average is basically computing a sum. And we said that there are protocols to compute the sum without sharing the individual records. We use these protocols over here. So that's basically it. This is basically what we do in this kind of a setting. And I'm going to skip the details, but we can make it fairly efficient. I'm going to skip the details. For vertical split, the situation is more complex, is not as trivial. So again, remind you that our data is split. Each party sees just some of these features. We do make the assumption that they are aligned in the sense that, right, if you think about each one of these features as a vector, right, the order of these vectors are the same for all parties. So we know that the first column the first row is related to subject 1, the second row is related to subject 2, and so on. And now we have a sort of a protocol in which we have the different parties. Each one of them computes some local information and shares it in an encrypted way with some coordinator. And the coordinator, basically what it does is kind of sums up the information from all these different parties and then distribute it again, if you want, I can go to the details, but I think it's late enough at night to skip the details. If you are interested, please come and see me, or I can send you the papers. But basically, it's possible to train even, we take this protocol, and then now we just add the encryption. These kind of weird brackets means that everything is encrypted. And we even experimented with that. So we can take data that is split between two centers, one in the east and one of the west of the US. The reason why you want it to be so spread apart, because when you work with these kind of protocols, actually one of your main bottlenecks is latency. So if you assume that all your data, if you run the experiment on the same data center, it doesn't make sense, right? So if the data is in the same data center, what I'm trying to hide from who, right? We're talking about settings in which I don't want to share my data with you, so it doesn't make sense that it's in the same data center. So you want to run the experiments in which the data is really split between two places, and the latency plays a crucial role. And here we can train logistic regression over 100,000 examples in about 6 minutes. So again, in the age of GPUs and all of that, that seemed like ridiculous, right? 6 minutes for training this kind of models, right? We can do it in a second. But you can't do it in a second when you want to keep privacy, right? And now again, if I ask you, okay, if these are two hospitals, what is our benchmark, our true benchmark in this setting? So imagine if these are two hospitals that are trying to build a model together. And they have to keep privacy because they have to comply with HIPAA and all of that. What is their other alternative to using encryption? Do you know what the other alternative?
Going physically.
No, you cannot go physically because the law, they have to comply with HIPAA. There is a law preventing them. The alternative is going to lawyers, signing an agreement between these two parties, Have you ever seen lawyers between two institutes signing an agreement in 6 minutes? I can tell you that I'm now working on a project with Kaiser. They want to share with me data which is anonymized. According to HIPAA regulation, it's anonymized. We're working for 4 years now. The lawyers are working for 4 years now, and I didn't get to see the data yet. So when you compare 4 years to 6 minutes, I think we're good. Right? So our benchmark is lawyer time and not competing all of that in the clear. So let me just summarize. You know, when you're working in a scenario in which you have to do some collaboration and there are some constraints, it's all about trust. You have to understand what do you trust, and if you trust, if you all trust me, then that's great, that easy. I'll do everything for you. But if you don't trust me, you have to rely on encryption, on mathematics, and there is a price to pay, but it's possible. It's possible to do that. And you know, private AI is about trustworthy AI tools, and this is what we're trying to build. Thank you.
Data, print out, then you perform only the fast forward there, and then send the encrypted result to the client, and the client will calculate the cost function and return the server the rating. And then
So let me repeat the question. So you're talking about training time, right? And you say basically, why don't we do something like the client? So we do in an encrypted way. We do the kind of the forward propagation phase, and then we send the data back to the client. The data will apply the loss function, and then we can apply the back propagation again. You could do that, and actually there are people that are doing that. The problem here is that is the number of iterations that you have to go back and forth. And again, when you do these kind of settings, the main price is latency. Right? And something interesting to keep in mind, if you look at the entire development in computers, CPUs, networks, whatever, we're making great progress in terms of throughput, but not so much in terms of latency. If you compare, for example, Ethernet, so 10 megabytes Ethernet, some of us have used it. I'm not going to point at anyone. But if you compare 10 megabyte Ethernet to 100 megabyte to 1 gig, 10 gig, so the 10 gig network has much larger throughput, but in terms of latency, it's about the same. Actually, if you look at the latency, I tested it. So the latency of sending a message between the east and the west coast of the US is about something like 2 to 3 times the speed of light. So you cannot expect to have much progress in terms of latency. So your main bottlenecks in this kind of situation is latency, and what you're trying to do is develop algorithms that don't have that many rounds, because
latency is able only to training it, not to the service.
True. So that's the service itself is one setting. We talked about it in the beginning. But if you want to do the training also efficient, you have to take into account latency. Other questions? Yeah.
Are you aware of any companies that develop a specific hardware for such FML computations?
So there is one little company called Intel, and AMD is another company.
Except for the SGX, they develop a specific hardware for that?
So the SGX and I don't remember how what the name of the equivalent technology for AMD are designed kind of a competition for that, right? And there are also all sorts of attempts to accelerate homomorphic encryptions by running them on GPUs, running them on FPGAs, and so on. So there are people working on that. Yeah.
I'm going back to the prediction part.
Yeah.
If you get a picture of number, you need to predict the number. And you get the number, you get the photo encrypted. How do you extract the picture?
So in the case of an image, you can think of it, what I get is just the pixels. Every pixel is encrypted. So for example, in the MNIST, it's each image is 28 by 28 pixels, which is 784, right? 784 pixels. You just get 784 encrypted messages.
But you have features to predict the number, right?
My features are these pixels. Okay? Okay, thank you very much.